Like to record this, so we are recording. So welcome back. Happy Thursday. I'm so glad 22 of us were able to join us. And what I like to show you right now is what I have posted on Canvas, on Blackboard, so you guys can see what's going on here. First of all, where do you find the pre-recorded, oh, not pre-recorded, by what? The live lecture recorded videos. They happen to be in what? Course content. And when you go to course content, you see these modules. Like for instance, this last Tuesday, you see where it says lecture video. And if you click on it, right, it will take you to what? To Tuesday's lecture. Somebody said, you know, the what? The videos are unlisted. But I think if you go via what? Blackboard, you'll be able to access it, because unlisted means what? If you have the link, you can access it, but the public cannot access it. But someone suggested, can I make it public? I don't mind. I have nothing to hide. So I will make it public. And then hopefully that will, make it accessible to you wherever you are and however you connect to internet. The other thing is, if you go back to so-called Blackboard right here, notice I have, first of all, did you guys notice I have posted a mock quiz here? Did you notice that? Here it is, and it's worth like 5 points. What is the purpose of this mock quiz? I just want to make sure that you guys know how to scan the 2 pages, make a single file, and convert it to PDF and what? Upload it on Blackboard. So next Thursday, when we have a test, we won't run into what? To technical problems. So if you just click on this guy, notice it says, what's the date today? Answer it. And then here it says, so when is our first midterm exam? So it's not mathematics. It's just like, make sure you answer these. I just want to make sure that you know how to scan documents, how to upload it in PDF as a single file. So that way we should be A-okay for next Thursday, correct? So we'll talk about that in more details in Tuesday, but the exam will be conducted during the class time, meaning it will be between 5 and 7, correct? So, you'll have 2 hours to finish the test. And once you finish it, then you can upload it on Blackboard. How would you do that? Well, when you kind of take the quiz, which that's what that is, then somewhere down here, where did it go? I can't see it. Yeah, where is it? I think that there was somewhere you could submit it. Do you guys see where it is? I kind of click on mock quiz. Yeah, okay. Mock quiz, yeah. And then where do you submit? I lost it. Do you guys see it? Where's the submit? Okay, let me see if someone can help me. Click on the title. Which title?
So if you go back and you click on the actual, like the black title, it'll send you to the.
This right here?
Yeah, where it says mock quiz, not real
Oh,
quiz.
mock, yeah. Okay. And there it is. Yeah. Notice it's like 5 points. And then you upload your browse my computer. And then you can submit. Where is the submit though? Oh, right here. It's right here. Submit. Do you see it? So could you kindly do that so I can see if you guys know how to do it? And to notice it's like 5 points to answer those silly questions. So that's my way of saying, can you do this? And here is the instruction, correct? Okay. Then you got review problems, okay? So that's you see where it says midterm exam, that's where I will post the exam next Thursday, right below mock quiz, and then review problems. There it is. These are review problems for midterm one, so if you click on it, so you will have around 20 problems. I'm not saying all of these problems will be on the test. The test will definitely will not have 20 problems on it, but it will be nice if you know how to solve these problems. And at the end, like page 3, I haven't solved the problems, but I have given you hints how to start the problems. If you still can't do the problem, next Tuesday, I will answer any question you have based on these 24 problems. Then again, I'm not saying all of these will be on the test. And the test covers chapter 12 and section 13.1 through 13.4 because your homework assignment is on, the last assignment is on 13.4, which is due this Sunday, I think. I'm not sure. Yes, it is. Sunday, 1 minute before midnight, it's due. Let me see if we have anything on the chat. Will the test have problems similar to how we solve those problems? Yes. What I will do is kind of change the numbers around a little bit, but I'm going to look at this review problems and pick problems from here, from these 2 pages, but I'm going to change the numbers around so it won't look like review problems. So I'm sure you guys can handle it. Yes, we should be okay. I hope everyone scores high. That would be my dream come true. So family and I, we can celebrate if you guys all get a high score on the very first test. Will the test have, that means the way to solve it shouldn't be different, or at least not too different. Yes, of course, of course, of course. It won't be too, it will be similar to this, not exactly the same, but it won't be like, oh my God, I don't even know where to begin, because supposedly, like over this weekend, I would appreciate if you take a look at the problems and try it as if they were test problem, see if you can do it. If you can do it, move on to the next problem and so on and so forth. You don't have to do every single problem, correct? Just try the ones which you think you have problem with. And if you still can't do it next Tuesday, I'll be more than happy when we have live meeting to go over every single problem which you will ask me to do. I will show you the solution in details, even though I have given you a little bit of a hint here, to get you going. But if you can't finish it, by all means, Tuesday, let me know so I can show you the full solution for any problem you have in mind. Is that a deal? Is that okay? All right. So what else? Let me see. What do we have here? Yeah. Very good. I think scanning will be better. What is this? Do we have to scan? No, no pictures. No pictures, just a scan. No JPEG, correct? Let me just switch the camera here so I can show you something. Check this out. Right here. Let me see. Okay, can you all see my screen here? Let's see. Okay, let me see. Okay, what I was going to show you is this app, which I have. It's called Cam Scanner. It's free. You can download it on your phone. I did on mine. So if you just click on it, once you download it, okay. Let me see if we get this. Notice there's a camera here, but the one you want is what? You want a batch, not single page. So you kind of go over the batch right here because you have multiple pages. Take the picture, you know, one at a time, then automatically what? This guy converts those pages into what? PDF and what? Um, as a single file. Then right from here, let's say I take, let's say, just for laughs and giggles, let's say I take a picture of this guy, then I take a picture of this page, then I am good to go. So I got 2 pages. Do you see it? So I'm going to go, what just happened here? And those are my pages. Do you all see it? There they are. See? Single file, but 2 pages. So this is like, where did it go? 1 out of 2. So there. So that's the second page. This is the first page. Okay, do you all see it? So it's free. Download it, and you don't have to have a printer or anything. Okay, what if I don't have a printer? Then you can what? Just like what I did. Take a clean piece of paper, put your name on the top, midterm number 1. You don't have to write the statement of the problems, just the solutions. Go number 1, here's the solution, box your answer. Number 2, here's the solution, box the answer. Take a picture of these guys, you know, make sure you convert it to PDF and then upload it, because it's hard to grade what? Picture as JPEG as PDF. Because what I will do, I will kind of open it with the iPad, and then I have the pen so I can grade it on the iPad and then upload it back to the Blackboard. So the minute I finish grading, you will see your own exam with my comments on it, so you can tell if you made any mistake, what kind of mistake was it, so you won't repeat those hopefully on the final. Are we good? Any other question regarding exam or anything else that you have in mind? Homework are due September 13, so please make sure you are done with this homework, yes? It's almost like 2 chapters worth of homework, because it wasn't about the last week. We were supposedly working on this since beginning of the semester. It's going to be like, what, 1 month already. So please make sure you meet the deadline, and I think we should be A-okay. Don't forget to review the problems for upcoming tests. All right. Is there anything else I should talk about before we start 13.3? Yeah. 13.3 is about arc length, which we used to call it the distance between 2 points on a line. But now this is the distance between 2 points on a curve, not on a line. If you remember, we going from point A to B, we could just construct this right triangle. Do you see it? So this is the difference between the x component, difference between y component. So based on the Pythagoras theorem, d is equal to what? D square equals this side is square plus this side is square. So if you kind of take the square root of both sides, you get this. Technically, we get plus or minus, but because we're talking about distance, so minus doesn't make any sense. So the idea is, what if you are on a curve like this guy, right? What if you are on a curve? Well, if you are on a curve, you select what? Consecutive, several random points on the curve, and then find so-called the distance between those 2 points on when you connect the points. In other words, if I zoom this, if I take this, notice what I'm doing. I'm not finding the distance on the curve, but I'm finding the distance of these line segments, which they happen to known as secant line. So these are the lines, they are not curves. Notice, so if I zoom this over here, zoom in, that's what I see. So instead of finding the length of the curve, I find the length of the secant line. How do I do that? Well, you know how it is. Let's say the delta S is what? The increment from P1 to P2 on secant line. So once again, you make the right triangle. So delta S is equal to delta X squared plus delta Y squared. Notice as delta X and delta Y gets closer and smaller, so what happens is what? The secant line gets closer and closer to the curve. Do you all see it? So that's basically the idea we will be using. Delta L stands for increment on the curve, okay? Whereas delta S is increment on what? Increment on secant line. Is that right? But they will be approximately equal to each other, if not exact. It all depends how close delta X and delta Y gets close to zero. The smaller these guys are, the what? The closer the what? The curve what gets to the secant line. At some point, it kind of looks like the secant line. So what happens is we say if delta X and delta Y gets small enough, that means they approach to zero, delta L is approximately the same as delta S, which is delta X squared plus delta Y squared. Remember, delta X is the same as dx and delta Y is the same as dy. So if you do these distances of these line segments, these subintervals, and do infinite many of them, like, you know, let the number of line segments approach to infinity, lo and behold, we get this formula, guys. There it is. There it is. This is in terms of what? Function of x. Okay, that is like if the curve was y equals y of x, okay, or f of x, which you have seen, I think, this formula in previous classes. The question is, what if the curve is given in terms of parametric equation? Well, in terms of parametric equation, then you would what? Write, what was it? Delta x. Notice what we had under the radical was dx squared plus dy squared, correct? But if the curve is given to me parametrically, what I will do is divide each of these guys by delta t squared and multiply by dt squared and multiply by dt squared. In other words, I haven't changed the value of what's under the radical. Notice I divided these guys by dt squared. I multiplied by dt squared. But the square root of dt squared is what? dt. So what happens, these guys stay under the radical, correct? And dt pops out. And lo and behold, this is formula number 2. This is like the length. Notice we show arc length. That's what this guy is called, arc length of a curve between point what? When t goes between a and b, equals square root of dx dt squared plus dy dt squared dt. You can also extend this guy to R3. So now if the parametric equation of the curve is a so-called space curve, so you are in 3D now, no problem. You just have to add dz over dt squared. Now, keep in mind the vector form of the what? Parametric of the curve is what? X of t y of t, what? Z of t, correct? What is the derivative? Is x prime of t, y prime of t, z prime of t, correct? What do you think this this integrand represents? How do you think we got from derivative to this? Does anyone see it? Because x prime is the same as what? Dx dt, and then this is dy dt, and this is dz dt, correct? So how do you think we got from derivative to this guy? What is the relationship between r prime and this? Can you all see it? Does anyone see it? Yes, no, maybe. Okay, did you want to take a wild guess? You see what the question is, don't you? The question is, somehow this guy looks like the derivative of my position function. But what is the relationship between derivative and what I have here under the radical and the radical itself? How are these guys related? Do you see it? Let me see. It looks like the antiderivative of the magnitude. Excellent. If you take the magnitude of what? R prime of t, very good, thank you. That will be exactly what you have under the radical, which is dx dt squared, dy dt squared, what? Dz dt squared, and dt. Yes, exactly that's what it is. In other words, if r prime is velocity vector, velocity, so here you get speed. So this guy is the speed. So if you take the antiderivative of the speed, that gives you the arc length of the curve. Do you all see it? Let me see. What do we have here? Sorry, Professor, I was having connection problem. No problem. Are you back? We are glad you are back, Nick. Yesterday, I was conducting my class to Long Beach people. All of a sudden, the Wi-Fi dropped me, so there was an interruption like for 5-10 minutes. So, hey, I hear you, no problem. I'm glad you are back. So do you see it? So if they give you the position vector, you take the derivative, which is velocity. If you take the antiderivative of a speed, that gives you the arc length of what? Of the curve. So this is arc length of the curve between what? T is equal to A and B. In other words, if this was a motion problem, I'm trying to find out how far the object has traveled on the curve. Let me just draw the curve here. How far this object has traveled. So this is like my object. This is like my curve. How long the object has traveled on this curve between times, let's say, A seconds and B seconds. Notice I can't show the time on the curve, so therefore that's what T's stand for. So between, I don't know, A seconds and B seconds, how far the object has traveled between these 2 points. Yeah, that's basically what it is. Okay, if that's the idea, then we can find the arc length of a helix. Remember, this guy is called helix. Remember? So this is the equation, cosine t, sine t, t. So what do? You write the parametric equation because this is the vector notation, correct? You write the parametric form. And once you write the parametric form of the curve, don't forget to take the derivative. Derivative of cosine is minus sine, sine is cosine, derivative of t is 1. Now use the magic formula, which is right here, or, take the antiderivative of the speed, depending on how you look at the problem. Mathematically is this, from physics aspect is like antiderivative of the speed, which this guy is a scalar. Anyways, so now you have to square these guys. This is not good enough. So once you find dx dt, dy dt, that's not good enough. Now the next step is what? Take dx dt and square it, which in this case is sine square of t. Take dy dt and square it. In that case, you get cosine square of t. And take dz dt and square it. In that case, you get 1. Add up these guys and put them under the radical. So that would be like sine squared plus cosine squared plus 1. But sine squared plus cosine squared is 1 due to the trig identity. So all you have is 1 plus 1, because this guy is 1, and then there was 1 squared. So that adds up to 2. So all you have to do is what? Integrate square root of 2 dt, which you and I, we both know the answer is what? Is square root of 2t, but then evaluate between, let's say they want you to evaluate this between t0 and pi over 2. So therefore the answer is what? The square root of 2 times pi over 2. And guess what? This would be so many units of what? Distance. Okay, of distance. You know, like so many feet, so many inches, so many meters, so many centimeters. Do you all see it? Do you see how we find the arc length? Yes? Question? Is that good enough, or should I do more example? What is your pleasure? So do you see how to find arc length of a space curve? That's what this is called, space curve. It just so happens it's that infamous curve called helix. Okay, so I just found out from here to here, where t is pi over 2, and at here time was 0, pi over 2 seconds later, the object traveled this much on the curve. Do you see it? Yeah, that's what I just found. So from point P1 to P2 on the helix, it's pi times the square root of 2 over 2 units of distance. So is that okay? By the way, before you find arc length, you gotta make sure the curve is smooth, because you don't want the curve to have sharp turn, or God forbid, a break in it. Do you see it? So the question is, how would I know by looking at the equation of the parametric equation of a curve? Let's say the parametric equation of the curve is x of t, let's say y of t, and let's say z of t, and let's say t goes between a and b. How would I know the curve? So the question is this question: how do we know? Do we know without graphing, graphing, if the space curve, you know, because remember last time we talked about this, the graph of these kind of vector value function, rain or shine, happens to be a curve. What is the simplest curve you can get your hands on? A line. That's also a curve. Yes? How do we know without graphing if the space curve is a smooth curve? Smooth curve. How do we know that? What's the answer? Right? Without graphing, can you look at the parametric equation of the curve and say, aha, this is a smooth, and hopefully there are no sharp turns, hopefully there are no gaps. Well, turns out if r prime of t is not equal to 0 vector for any t in the domain of what? Of r of t, then what? Then we can make sure what? Then the space curve will be what? Smooth curve. smooth curve. Is that right? So that's basically the test. Take the derivative. Make sure the derivative of the position function is not zero for any t in the domain of R of t. So this is basically the definition of what? Smoothness. Then you can bet your money the curve is smooth, so you can go find arc length. We no longer call it what? What is it? Distance. We call it arc length. Do you see it? The question is, can we do one more example? Of course we can. The only problem is I don't have any example offhand. So let me pick one and see if I can show you one more example by all means. Okay, how about, let's say we have this vector value function. Let me just write the problem first. It is 2t, t squared, 1/3 of what? T cube. 1/3 of t cube. And t goes between 0 and 1. So I don't know if you guys can see it. This guy is 2t. This guy is t squared. This guy is 1/3 of t cube. And this is your vector value function. And however the graph looks like, so the assumption is what? Is a smooth curve, God willing. So question is find the arc length of this space curve when t goes between 0 and 1. So that's basically the idea. So the clue is find the arc length. So begin by writing the formula so you would remember what the formula is. Okay, the formula is this right here. Is that right? What is the formula? The formula is what? Antiderivative. T goes from a to b, square root of dx dt squared, dy dt squared, dz dt squared, don't forget to square dt. That's the formula. Okay. A function on R2 can still be smooth as long as the derivative, yes, correct. Remember, we had that theorem back in the good old single variable calculus. Differentiability implies continuity, but continuity does not imply differentiability. Because if you remember from single variable calculus, the graph of absolute value of x had a sharp turn at 0. Notice the graph is continuous but not differentiable. However, if the function is differentiable, then it's continuous. Yes? So, what is the parametric equation? It's what? T squared, z is equal to 1/3 t cubed. So this is the curve. T goes between 0 and 1, correct? What is, I think it's because the standard vector that's between the origin and space curve would have no value and would cause a blank spot in the curve. That's true, that's true. So take the what? Derivative, that's 2. Derivative of y with respect to t, that's 2t. Derivative of z with respect to t, that's what? T squared, correct? But that's not good enough. Now you have to square these derivatives. That's not good enough, correct? Take the derivative, square these guys. Don't forget to square this. That's 4. That's 4t squared. That's t to the 4. Correct? But now you're ready to what? Plug it in into the formula, correct? So this would be square root of, what is this? 4 plus 4t squared, t to the 4, and outside of the radical you have dt. Okay, How do we integrate this? Any idea, guys?
Factor it.
I'm sorry. Oh, yes. Yes, indeed. Yes, indeed. Yes, indeed. Yes, indeed. So this would factor as t squared plus 2. There. And the square root of this guy squared is just what? 0 to t, which is t squared plus 2 dt. The radical sign wipes out the power of 2, correct? So what do we have? Oh, this is easy. That's t cubed over 2 plus 2t going from 0 to 1. That's 1/3 plus 2, which is 7/3. There it is. Easy peasy. Do you all see it? Yeah, we good? So this is called arc length, and it's denoted by what now? The capital letter L. Actually pretty easy. Yeah, it is. That's why I kind of went through this fast, because it's really no thinking is required. You just take the derivative, you know, raise them to the power of 2, add them up, put it under the radical, you're good to go. All right. You remember this unit tangent vector, which is defined as r prime over its magnitude. So if you have a smooth curve again, here is some point on the curve, unit tangent always what? Points to the direction of the curve, correct? So that is, so this guy points to the direction of the curve. In physics classes, we call the path of the motion. So sometimes when you have like, you know, like helix, do you guys remember this curve? Sometimes for whatever the reason, we like to measure the bend on our space curves. Do you see it? So the question of the day is, how do we measure, the amount of bend on a space curve? As a matter of fact, this also works for any curve. It doesn't have to be space at a specific point on the curve. Okay. In other words, I can go back to algebra classes and find out, oh my goodness, the equation of this guy is y is equal to x squared, which is a parabola. So I want to know at 0, 0, how much bend do I have on the curve? Ladies and gentlemen, that idea is called curvature. That's C-U-R-V-A-T-U-R-E. It's pronounced curvature, and it's denoted by the Greek letter kappa. It's not, it's Greek K. Okay. So in R3, it is, assumption is you have what? You have a parametric equation of the curve. It is magnitude of what? R prime cross with R double prime over magnitude of R prime to the power of 3. This is the formula to find the curvature of a space curve, provided the curve, the equations of the curve is given to you parametrically, yes? Like so. In other words, you have what? R of t is equal to what? X of t, y of t, z of t, parametrically. If that's the case, you take its derivative, you take the second derivative, cross product, that's what this is, it's cross product, and then you take its magnitude. So as you can tell, what? Curvature has to be greater than or equal to 0, and this would be always a number, scalar. You all see it. So what do you say we go back to our good old what? Helix here. Okay, remember this guy was t is equal to pi over 2. I'd like to know how much bend do I have right at this point P. Right about here, how much bend the curve has. What is the measure of the bend at this point, correct? Calculate cross product by hand. I don't know how else do you calculate cross product. Do you have some sort of program or something? I don't, so I do it by hand. I don't know about you. But if it is required, like, you know, to find cross product of two vectors, I like to see the work, right? But if it is embedded in part of the solution of a certain other problem, then you can do it. Oh, there is a cross product calculator on, oh, Symbolab. Oh, okay, I guess, but make sure that you show work. Don't just drop the what answer on the paper, correct? All right. Okay. I usually grade the procedure, not the answer. So be careful. Answer without work in you know, in a very obvious ways, like, you know, the problem wants you to compute something, you just give an answer and box your answer. That really doesn't fly, because the whole idea is for you to show the steps. Of course, you can avoid all the obvious steps, but in general, try not to drop an answer out of the blue sky. Show some sort of work behind it, that's all. All right, so how do we do this? Well, what you do, you remember the equation of the helix, the parametric equation of the helix was, what was it? X equals cosine of t, y is equal to sine of t. Of course, this is the one which opens along the what? Along the z-axis. So I like to find the curvature at pi over 2. This is the amount of the bend. Yes, bend. All right, so take the derivative. That would be r prime, which is what? Minus sine of t, cosine of t, 1. Take the second derivative. That would be like what? Minus cosine of t, minus sine of t, 0. Now, take the cross product. Okay, like so. Remember, ijk. Okay, so you got minus sine of t, cosine of t, 1, minus cosine of t, minus sine of t, 0. You see it. Okay, so let's say I have done this and I came up with 1, 0, 1. Okay, so so what? Let's say I evaluated this guy at t is equal to pi over 2, and I came up with negative 1, 0, 1. So the formula says what? What is it? This is how you write kappa, see? There. So it won't look like K. So kappa, that means curvature at pi over 2 equals magnitude of what? Of what? This vector. Okay, over magnitude of this vector cubed. Magnitude of this vector cubed. You know, r prime. That's the formula, remember? Right here. See? Magnitude of the cross product over magnitude of r prime cubed. Okay, on top you get the square root of 2, that's 1 squared plus 0 squared plus 1. At the bottom you get the square root of 2 cubed. So one of these square roots wipes out one of these guys. So at the end of the day, you get 1/2. Okay, there it is. Notice you get a positive number. You all see it? So what did we find now? We just find out at pi over 2, right about here, the curvature is 1/2. This is the measure of the bend. But I have a problem with that. The problem is, what does this tell me? Okay, I don't have any point of reference to compare this to say, oh my God, I have a big bend or I have a small bend. So what do I do with this? Well, to answer that question, what you do, you kind of draw a circle at that point tangent to the P like this. Okay. And that circle has a name, is called what? Osculating circle. You know what osculate is? Osculate comes from Latin word is kiss. So this circle is gonna kiss that point, what? Right there. And its radius, the radius of this circle, so we're going to show the radius by the letter rho, that's the Greek letter rho, is always reciprocal of the curvature at that point. In other words, the radius of the osculating circle is reciprocal of the curvature. What does that mean in our case? Remember, I came up with curvature. What was it? What was my answer? Do you remember? It was what? Curvature at pi over 2 came up to 1/2. So the question is, how much bend do I have? I mean, this doesn't really do anything for me. Yes, it's the correct answer, but I want to get a feel for it, you know, something tangible so I can get a feel for it. So what you do, you draw this oscillating circle at that point, make sure it's tangent. And the radius of that guy is reciprocal of the what? Reciprocal of the curvature, so reciprocal of 1/2 is 2. So now you know exactly how big the bend is. The bend is as big as a circle with radius what? 2. So that gives you a feel for how much bend do we have at that point of the curve. Do you see it? So osculating means kiss. So the circle is kissing the what? Curve at point P, and its radius, usually they show it with the Greek letter rho, is reciprocal of the curvature. So now you know. Here is a question for you guys. Who really cares about the bend on the curve in real life? What do you think? Who cares? Don't tell me we do because it's in section 3.3. Yes, I know. But who else cares in real life to find the amount of bend on any curve?
People who design train tracks or roller coasters or something?
Exactly, exactly. This is one of the fundamental ideas behind designing the roller coasters. Yeah, you can't just bend the track any old way. You have to bend it so people won't fall off from the roller coaster. So these bends, they are very mathematically are computed. So there is an engineering behind this. It's not like, well, let's bend the curve and the track and let's hope nobody will fall. No, these are so accurately designed. So when they go at a higher speed, nobody falls. Of course, they have seatbelt, but besides the point, these are very computed and calculated what? Bends. So that's one application. Civil engineering, when they design bridges and even like, you know, beams, they need to know how much bend each beam has. so they can prevent of that beam, you know, breaking at some point or whatever. So they have to compute this kind of stuff beforehand before they actually build that, whether it's roller coaster or bridge or whatever. Do you see it? Here's my next question. What is the curvature of a line? What is the curvature of a line?
0 at every point on the line.
I'm sorry, one more time, please.
0 everywhere on the line.
Everywhere it's 0. There is no bend on the curve. So the curvature of a line is rain or shine 0. And because what? In a circle, okay, the radius is reciprocal of the curvature. So, or you could say curvature is reciprocal of the radius, doesn't matter. So the bigger the radius, the smaller the curvature. The smaller the radius of the circle, the bigger the what? Curvature. What does that mean? This guy has more curvature than this guy. Do you see it? This has less curvature than this guy. Why? The lesser what? More curvature. The lesser the what? Radius, the higher the curvature. So this guy has higher curvature. So if this guy has curvature 2, this guy is curvature 1. Curvature 1 is greater than curvature 2. Why? Because of this relationship. The smaller the radius, the higher the curvature. And a straight line doesn't have any curvature, so curvature makes sense to what? To say it's 0. Okay, that's fantastic, but I have one more question for you. How about if you have y is equal to x squared? Okay, in other words, I'm taking you back to the previous classes, and I want you to find the curvature at 0 of a parabola. How would you do this? How would this crazy formula apply? Where did the formula go? Yeah, where'd it go? Let me see, right here. How would I apply this crazy formula to this guy, which is what? Y is equal to x squared. Any idea? You see where I'm going, right? Remember, I had that crazy formula, but how does that formula applies to this guy? Does anyone see it or any suggestion?
You can convert it to a parametric.
Exactly. How about if you convert it to parametric? That would be 1. Could you give me the parametric equation of a parabola? Remember, there are more than one answer. What would it be? What would be one way to parameterize this? So in other words, how do you parameterize y is equal to x squared? Remember, it's not unique, so that means you can parameterize your parabola your way, I can do it my way. At the end of the day, we're talking about the same curve. So give me your version. What would you say?
X equals root y.
Okay, that's fantastic, but I hate radicals. So how about this? Would that do it? Let x be t, and y is t squared, and t goes between negative infinity to infinity. And if you select like 0, you are here. If you select 1 for t, 1 second later, you are here. So therefore, the direction of the curve is this way. It goes from left to right. Remember, these are, because it's parametric equation, so they are orientable curve. In other words, it's not just a parabola, it's a parabola with a direction. Okay, how do I find this? Well, you can use this, or you can use this, which is designed for what? for functions of x. This formula, check this out. It's a little bit complicated formula, but it does the job. So there it is. Absolute value of f double prime divided by what? 1 plus f prime, quantity squared, then the entire denominator to the power of 3/2. This formula is used when y is a function of x. So you don't have to use that crazy formula. And also it will be function of x, not t. Do you see it? So if I use this formula, what would be the curvature at what? 0, 0. So right here, at x0, y0, this point, which happens to be called the vertex, how much bend do I have on the parabola? Okay, that's easy. All you have to do is what? Kind of take your function, take two derivatives, and now you're ready to roll this. And what is this? Absolute value of 2, 1 plus what? 2x squared to the power of 3/2. There. Is that right? Now don't forget, we like to evaluate this at x what? 0, y0 at the origin. Okay, so k of 0 is 2, because remember, sometimes this comes up negative, so you need absolute value. 1 plus that guy is 0, and that's 3/2, which is 2 over 1 to the power of 3/2, which is 2. That's how much bend do you have. Okay, if anyone asks you, hey, what does that mean? Okay, I see you got a 2, but what does that mean? Can you show me a picture so I can get a feel for how much bend I have? Immediately draw your oscillating circle. Make sure it's tangent to that point. And tell them my bend is as much as this guy, whose radius is 1 over k, which is 1/2. That's how much bend do you have. Because this number really, what am I supposed to do with 2? Okay, so what is it? How much bend do I have? Well, your bend is as much as the bend on a circle whose radius is 1/2. There you have it. Do you see it? Yeah, we good? So with that, you can go ahead and what? In the parties and gatherings and anniversaries, impress people by finding the amount of bend on natural log right about here. Why don't you find out what the bend is there, which happens to be 1, 0, using that magic formula which we just went over. Do you see it? So now you have it. Yes? All right. Any questions so far? How are we doing, guys? Yeah? We good? So what have we learned so far? We learned about arc length of a curve. We learned what it means, what? To say, what was it? If a curve, how do you know if a curve is smooth? And we just learned how to find the curvature, which measures the amount of bend on a what? Space curve, or a what? Or a plane curve, which happens to be drawn on the x and y axis. Isn't that fascinating? All right. I'd like to introduce 3 special unit vectors. 3 special unit vectors. Of course, when you take the test, you're taking it at home and you have all the formulas available, so luckily you don't have to memorize. However, when we were on campus, I used to let students to bring what? Index card, 3x5, and they could write any formula or any solution their heart desires to the test. For right now, you have all the resources available to you, so there is no need to memorize anything, right? All right. Ladies and gentlemen, the next topic is about 3 special unit vectors. One of them is called unit tangent. We know what that is. It's r prime of t divided by its magnitude. The other one is called unit normal vector, and that's defined as what? T, the derivative of the unit vector divided by its magnitude. The last one is called binormal vector, which is denoted by B, and that's T cross N. And yes, the order matters. Do you see it? So these are three important unit vectors in motion problems. Okay. Just got to remember, is the bend. Oh, yes, 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 yes. All right. So whenever you have a motion problem, like let's say an object is traveling on a smooth path, these three vectors are always with what kind of influences the motion. Okay. T is what? Is direction of the motion. So unit tangent is always in the direction of the motion, always. So notice the motion is this way, so is the direction of the unit. In normal vector, it indicates how the curve turns, the turn, not the bend, but the turn. Question is, how did you know this is normal but not the other way around? How did you know that? In other words, what made you think to draw the normal at this point this way? Okay, not this way. How did you know that? Right? Because for sure, the unit tangent, we know it goes in the direction of the what? Motion. That's given. But the question is, how did you know the normal goes this way, not up? Turns out we have something called principal unit normal vector. So this is principal. Principal means we always draw the what? Normal from the concave what? Down part of the vector space, curve. So if the curve goes like this, we draw the normal vector this direction. If the curve concaves down, we go this direction, not up. This is because of our adoption of so-called principal unit normal. So keep that in mind. It always what? Generates or initiates from the concave down part of the curve, not up. Okay, that's just a rule of thumb in the land of multivariable calculus or vector calculus, as a matter of fact. So what the T indicates? The direction of the motion. What does N indicate? How, what? The path turns. And what's up with the B? B is the cross product of what? T and N, so it's perpendicular to both T and N. But it doesn't do anything for the motion, but it's associated with something called torsion. I think we mentioned this last time. And that's the amount of twist in the curve, not bend, but twist. Do you know what the difference between bend and twist is, guys? Yes, can I have a thumbs up? The difference between bend and twist. Does anyone know? Okay, this would be a good time to let me know the difference between bend, the curvature, and torsion, which is twist. What's the difference? Not formula-wise, in real life.
Wouldn't it be how the curve moves off the plane of movement?
Right. So what happens is, I don't know if you guys can see this. Okay, no, that's not. Oh, okay, maybe I should do this. You see, suppose this is my paper, correct? So here we go. And you put your what? Both hands on the end of the paper, which I rolled here. Okay, you see it? This is bend. See, I'm bending it. I don't know if you guys can see it. See, I'm bending it. Twist, you hold one side of the paper, let me see, with one hand, and with the other hand, you twist. Do you see it? Bend, you put both hands on what? Both ends of the paper and what? Bend it. Twist, you hold it with one hand, with the other hand, you twist. And that phenomena is called what? Torsion. So the bend has to do with curvature, twist has to do with torsion. And the torsion, unfortunately, has the same what? Notation as torque, but torque was function of what? This guy is a function of arc length, where torque was function of T. This guy is a function of arc length, S. And this is how it's related. The derivative of the binormal with respect to the arc length. So remember, S stands for arc length. Okay. In this context, times the normal vector. Is this something I should know? No, you don't, but I'm just telling you, this is how B affects the motion. It is associated with any twist on the path. Okay, not the bend, but twist. So how do you find these guys? Remember, these are the definitions, correct? So T is what? R prime divided by magnitude. N is what? T prime divided by magnitude. B is what? T cross N, and the order matters. It's not N cross T, it's T cross N. So with that in mind, how would you like to see what? How to compute these three important what? Unit vector. So let's go back to our usual helix because it's easy. Cosine of t, sine of t. And let's say we like to what? Find t of pi over 2. Okay, n of pi over 2, and b at pi over 2. So in other words, I have a helix, which is a space curve. I was asked to find a unit vector, normal vector, binormal vector at what? T is equal to pi over 2. Okay, so how would you do this? Okay, what is T? What is the definition of unit vector? The definition of unit vector is what? R prime divided by its magnitude. Okay, that's the definition. When you have two equal sign with a triangle on top, that just means definition in the land of mathematics. Okay. Yes, sometimes some books they use S for arc length as well as L. So it depends on which textbooks you're looking at. So in our case, R prime is negative sine of t, cosine of t, 1, divided by its magnitude. Well, because I was asked to what? So that would be minus sine t squared, cosine squared, plus 1 squared. Let me just zoom in so you guys can see what I'm doing here. Okay, so now I'm going to evaluate this at t equal to pi over 2. So I'm going to get negative 1, correct? 0, 1 over square root of 2, because sine squared plus cosine squared is 1, and then there is 1 squared, so you get 2. So therefore, the unit tangent evaluated at pi over 2 is 1 over square root of 2, negative 1, 0, 1. You can also forget about this, 1 over square root of 2, just say, there it is. There goes my unit tangent. This is just a scalar which is attached to it. Okay, next, unit normal at pi over 2. Well, that would be like what? Derivative of the unit tangent divided by what? Its magnitude. But you can't go from here. You got to go back here now. So remember the unit tangent vector came up to be 1 over square root of 2. What was it? Minus sine of t, cosine of t, and 1. So now I have to take the derivative of this guy. Take the derivative before you evaluated it, okay? Let me just zoom out so you guys can see. So 1 over square root of 2 goes for the right. Derivative of the unit tangent is minus cosine, and this is minus sine, and that guy is 0. Now, evaluate this at pi over 2. You get 1 over square root of 2, 0 minus 1, 0. So, what do we get? We get 1 over square root of 2, 0, negative 1, 0, divided by magnitude of the sky. What is the magnitude of the sky? Magnitude of what? T prime, what? At pi over 2 is what? The square root of 1 over square root of 2 comes out of the radical sign, so that's 0 squared, negative 1 squared, 0 squared, which is 1 over square root of 2. So in turns, these guys cancel. So therefore, the normal vector at pi over 2 is simply 0, negative 1, 0. Okay, so you got the unit normal, you got the unit tangent. So when you take what? The cross product of unit tangent with unit normal evaluated at pi over 2, that gives you binormal vector. So in this case, this would be I, J, K, negative 1, 0, 1, 0, negative 1, 0. Did you notice I dropped this 1 over square root of 2? Because that guy is just a scalar. So it doesn't really put any dent in your answer. So either you carry this with your computation or drop the scalar. It won't put any dent in your final answer. So turns out this guy is 0, 1, 1. So there it is. So now we got the unit binormal, and we have the unit normal, we have the unit tangent. Question is, how would you show all of this on the picture? Okay, how would the picture look like? You know, show these vectors on your picture. Well, remember, this is my helix right here. Okay, remember at pi over 2, we are here. Okay, let's say that's pi over 2. That's the point. Okay, so now at this point, you draw these what? Unit vectors, negative 1, 0, 1. And then the other guy was what? 0, negative 1, 0. And what was the binormal? It came up to 0, 1, 1. So at this point, draw these. When you draw these guys, what you do, you draw what? A coordinate system. So there goes y and z and x. So at that point, draw the coordinate system and now draw these vectors. Okay, because these are what? Position. They are not position. They don't initiate from 0, 0. They initiate from here. In other words, as if you transferred or translated the origin to point P, now your job is to, or my job is to graph these unit vectors. Okay, so what is the first one? Negative 1, what? 1. So I will be right there. So that's my unit tangent. Notice it's kind of sort of what? Tangent to the what? Space curve. And it shows the direction of the what? Motion. Okay. But then again, at point P, draw 0, negative 1, 0, which is this guy. That's N. Okay, there goes N right there. 0, negative 1, 0. Go 1 unit to the left of the y-axis. This is the y-axis. Okay, notice it's pointing from the concave down part of the curve. What about binormal? It's 1, 1. So 1, 1, I would say it will be somewhere out there. So that would be like binormal. So this is 0, 1, 1. So 1 unit to the right, 1 up. Is that right? So there you have it. In other words, these three vectors, they always follow the object in any motion problems on a curve. So it is so famous, it has a name. It's called TNB frame. Okay, TNB frame. It always follows any motion. Okay, there it is. Wherever the object is, TNB follows. Always, every point on the curve. Okay, that's basically behind the scene. You never see it, but it's there. Do you see it? In other words, these guys, they are so important in physics classes or motion problems, which we have a name for these guys. Suppose this is what? This guy right here is what? Is TB plane. Okay, that's TB plane. This is what? BN plane. Okay, TB plane, BN plane, and the other guy is called what? What is this guy called? NT plane. So why do I care about these planes? Well, turns out if you have a curve motion, you know, a space curve, these guys have names. This TN plane is called osculating plane. That is the plane which what is determined by these two vectors, unit tangent and unit normal. The plane which is determined by what? N and B is called normal plane. So this guy is called normal plane. And the plane which is what? Which is determined by T and B, okay, T and B, it is called what? Rectifying plane. Turns out in physics classes, most of the motion occurs in oscillating plane. And this is like that oscillating circle right here at this point. So majority of the what? Motion occurs in this plane, not these guys. In classes like called differential geometry, you get to deal with these kind of planes. For instance, which of these vectors do you think is normal to oscillating plane? Which of these three vectors is a normal vector to oscillating plane? Can you see it? Yes, indeed, it's B. The normal vector to what? To normal plane is T. The normal vector to TB plane is N. So sometimes they give you a point on one of these planes and they ask you to write the equation of this plane. We are not going to do that, guys. Don't worry about that. So do you see it? Yeah? We good? Everyone is okay? Yeah? Any questions so far? This was just some side story, so you are not responsible, but make sure you know how to find unit vector, normal vector, binormal vector. These are the three important vectors which affects the motion. This guy is in the direction of the what motion. This guy is like how the path turns, and this guy is associated with torsion. So that's basically why I brought it up. Okay. About 5 more minutes of your time so we can go home a little bit early tonight. And this would be a quick kind of like coverage of 13.5, but I will just mention it, but I don't think I'm going to put any problem on the test. Basically, this guy is called tangential and normal component of acceleration. Okay. Let me just give you a 5 minutes story so you guys can tell what's going on here. If the motion happens to be linear, that means you are what? On a what? Straight path. If so acceleration is scalar derivative, so it's not a vector, it's a linear, so acceleration is dv dt. So this is called scalar derivative. Scalar derivative, correct? However, when the motion is in 2D or 3D motion, so here, if the what? If this guy is traveling on a straight line with a constant speed, so suppose this guy is traveling with constant speed, or let's say you're traveling on 405 north with constant speed, what would be your acceleration?
0.
0. That's not true when the motion is in XY plane or 3 dimension. Why? Because if this is what? Your path of the motion, velocity, what? Changes its direction. Do you see it? Also, it changes its magnitude. So those two factors influences the acceleration. So in this scenario, even though the speed might be constant, acceleration is not 0 because the velocity vector changes its direction as well as its magnitude. So those directly affects the what? Acceleration. So therefore, what we have is this. So if this is acceleration, okay, at any given time, let's say this is acceleration, okay, let's say either in 2D or 3D, acceleration, because the velocity changes its direction and what? Magnitude, so does acceleration. So acceleration turns out it decomposes itself into two components. Let's say this is my acceleration, let's say this is my unit tangent. Let's say this is my normal vector. Okay, this is my normal. Is that right? Let's say this is the normal vector. This is my what? Unit tangent. Acceleration, because the velocity changes its magnitude and direction, acceleration also follows the same concept. So what happens, it gets decomposed into what? Two, what? Let me just do the acceleration a little bit this way so you guys can see. Two components, okay? Two components. Portion of it will be what? Along the motion, like so. There. So this is T, and this is what? This is like what? This is like horizontal component of what? Acceleration. And portion of it will be along the normal vector. And this portion is called what? This right here is called what? Vertical component. Component of what? Of acceleration. Do you see it? So there is no such a thing, acceleration is zero, even though the velocity is constant, because the velocity in 2D or 3D changes its direction as well as its magnitude. And those directly affect acceleration, because acceleration is what? Derivative of velocity. Okay? So what happens is acceleration in higher level, higher level physics classes, I'm sure you have seen this, it decomposes into what? This guy, which is called tangential component, plus what? Normal component. So this would be uh, tangential and normal component. So let me just erase this. Okay. So it would be some scalar times unit tangent times some other scalar times normal vector. This AT is called tangential component. AN is called normal component of acceleration. So notice we decompose the acceleration into two parts. Would acceleration be zero in R3? No, never. Because velocity is what? Changing its direction and what? Magnitude. Therefore, it's not constant, you know, even though it's constant, but it's about vector, not a scalar. Notice right here, I took the derivative in scalar derivative. So if this guy was numbered, this is zero. But in what? In 3D, the vector is given to you in terms of x and y and z component. So even though the what velocity might be constant, but acceleration is will not be zero, because it decomposes itself into two what components. In other words, what I'm trying to say is maybe the what? The tangential component of acceleration be zero, but the normal won't be. And the quick example of that will be a circular what? Motion. In circular motion, even though velocity is constant, let's say the velocity is constant anywhere along this curve, circular motion, acceleration is not zero. Where is the acceleration? Can you guys tell? Yeah.
Pointing towards the center of the circle.
Exactly. This guy, the tangential vector component is zero, so this guy goes to zero land. But still, you still have a normal component. That's why it can never be zero. So in other words, there it is. There is the acceleration. There. Even though the velocity was constant on a circular motion, acceleration is not, because the tangential is zero, but the normal is not. All the what? Concentration of acceleration is towards the center. And this guy has a name. What was it called? What was this force called? Pointing to the center? What was it called?
Centripetal force.
Excuse me?
Centripetal force.
Centripetal force. And that's precisely what you would experience in what? In your car when you make a sharp turn, okay? What happens is, up there in physics classes, they go AT is equal to what? The derivative of speed, which is shown by second derivative of the arc length, And this is physics formula. Mathematically, I'm going to show you a different formula. This is what they show in physics. This is curvature, and this is like what? Velocity squared. So in physics classes, this is how the formulas for what? Tangential and normal component of the acceleration is equal to. Not in our class. We have different kind of formula. We're gonna simplify this and change these to vectors. So what is the meaning of this? The meaning is when you make a sharp turn with a high speed, when you get in off the exit on freeway, what happens is this guy is 0, but this guy, what? Points to the center of the what? Road. And if your what? If your velocity is doubled, your acceleration will be what? Quadruple. Do you see it? So that's why those people who get off the exit with a higher speed, the car turns around, flips. I know someone who did that, and boy, she got messed up. I mean, her face, you can't even recognize her no more because she got off the exit with a higher speed. And what happened, the car flipped and she got injured, and oh my God, don't want to even think about it. So that's basically what happens. If you double your speed, acceleration quadruples. So the car kind of like flips. It won't stay on the road anymore. And that's not good. However, let me just quickly give you a mathematical formula and we should be okay. So acceleration, it decomposes into ATT and ANN. So this is the tangential component, this is the normal component, some scalar times what? Tangent, unit tangent plus some scalar times normal, but AT and AN, these guys are scalar factors. These are numbers. What is it equal to? It's equal to, this guy is equal to velocity dotted with acceleration divided by speed. This guy is magnitude of velocity cross acceleration divided by speed. In other words, if you have an acceleration, let's say I give you an acceleration such and such, you can always divide it into two parts, something times t plus what? Something else times n, so you can decompose it. And as you notice in the circular motion, the tangential component goes to never land, but the normal is there, so it's never 0. Do you see it? So that's basically what that is. So I just want to mention it to you, so if you can get a kick out of this, but it won't be something you have to worry about on the test. We good? We okay? Is there any question about anything I said or wrote this afternoon since the beginning of the class? That was, kind of a crash review of 13.5. As I said, don't worry about it. Just know acceleration, what? Decomposes to tangential and what? Normal component. Any question, guys? So we good? Yes.
What the practice test that you have for us? What day is that due on?
That's okay. Thank you for bringing that up. Let me just come back to you guys. Okay, here's the deal. Those review problems are for you to get ready for the upcoming test, which is next Thursday, which is a week from tonight, correct? However, if you do those problems, knowing that I have given you some hint, but you take it all the way, do it all the way and get an answer, box your answer, that would be extra credit. and it will be due the night of the test. And that would worth like 10 points. So do those problems using my hints, because I haven't solved those. I just gave you a hint how to do it. Do it, complete it, and the night of the test, what? Upload it on the Canvas, and you get extra credit. As a matter of fact, I will create a file for extra credit, 10 points, and then you can upload it. How's that? Is that okay with everyone? So for tangential acceleration, since its constant, the tangent is 0, while the normal is still, yes, the normal is not 0. That's why it never, ever 0 acceleration, even though the speed is constant in what? 2D or 3D. I mean the one we have to put our name and date. Oh, the mock quiz, you mean? Hopefully sometimes before the test, so you guys can see if you can upload it. So preferably before the test, sometimes between now and next Thursday. I didn't put any deadline on it. Okay, what else? You're welcome, you're welcome. Anything else? Okay, guys, have a great weekend. Thank you so much, and good night. Take care.
Thank you, Professor.